Okay, so we are in causal inference in statistics. Okay, this book right here. And we are on question 2.41, which is a multi-parter. So we'll go through each of these. But they're all talking about this DAG right here. Okay, and so you can read the DAG for yourself. If you read the caption here, it says all U terms not show. Okay, and the U terms are error terms. Okay, so in other words, each one of these nodes has another node that's affecting it. That's an error term that we are not looking at, that we can't measure, for instance, maybe. But the error term for Z1 only affects Z1 and nothing else. So it's independent of everything except for Z1. And so we are going to, so we can ignore all of the error terms. Okay. All right, so let's start with A here. So for each pair of non-adjacent nodes in the graph, find a set of variables that d-separates that pair. What does this tell us about the independencies in the data? Okay, so what do we mean by non-adjacent nodes? Well, let's look at an example here. Okay, so we have x and y. All right, now these are non-adjacent because they're separated by other variables. Right, there's variables in the way of me getting from x to y. However, x and w are not non-adjacent. They are adjacent, right? Because there's no other variable separating me from them, okay? So we want to find a set of variables that d-separates each pair of non-adjacent variables. So what do we mean by d-separates? Well, we want to close down all paths that go from x to y, or any non-adjacent set of variables here, okay? So let's start with a simple one, okay? Let's start with w and z1 here, okay? So these are non-adjacent, of course, all right? So we want to close down all the paths between them, okay? So one of the open paths is w x z1, okay, and another open path is wx z3 z1, okay. Well, we can close down both of those paths by simply conditioning here on x, right? Now you may say, but isn't there another path that goes like w y and then z3 or z2 and eventually to z1? And the answer is no, because y is a collider here, right? So this path, those paths are already closed because y is a collider between w and the other paths out of y. Okay. So let's do one more complicated one. So let's take x and y here. Okay, these are non-adjacent, like we've already addressed, and we want to d-separate them. All right. So here's one path that goes from xw to y, okay, and this is just a pipe, and we can condition on w to close down that path, so that's easy, okay. But now there's these other paths that lead from x1, say, to z3 and y, or x z3 z2 y, or x z1 z3 y, okay. And so we need to close down these paths. As well. So whether we go from z1 to z3 to y or z3 to y, z3 is the common node here. So let's condition on z3. Okay, so I need to block z3. But now when I block z3, I've closed the path from z1 to z3 to y, but z3 is a collider between z1 and z2. So now by conditioning on z3, I open the path from x to z1 to z3 to z2 to y. So now I need to additionally condition on z1 or z2, okay? And so that's what's represented here, right? I condition on w and z3 and either z1 or z2, okay? So you can go through the rest for yourself. If I've made a mistake, let me know. It's very easy and to make mistakes here, either because of not seeing the paths clearly or just simply making a typo. All right. Part B is we want to repeat question A, but now we only measured a subset of variables here, Z3, WX, Z1. Okay, so I'm not going to really go through this because all we need to do is we need to look at our answers to to Part A, and only grab the answers where all that we've measured are these variables right here. Okay, so it's just a subset of here. Okay, and so if you could answer Part A, you can answer Part B. Okay, I guess where this is relevant, is that sometimes you have a system and there are variables that you know exist but you cannot measure or are too expensive to measure, and so you need to work around those constraints. Okay. Part C here. For each pair of non-adjacent nodes in the graph, determine whether they are independent after we condition on all other variables. Okay, so for instance, I have x and y, and now I'm going to condition on everything else. W, z1, z2, z3 are x and y independent. Okay, so let's go through this. So if I condition on, so I want to look at x and y, and I want to condition on everything else. I want to know if that makes x and y independent. Okay. So if I condition on W, that's a good start, right? Because we're blocking that path. Okay. And now I'm going to condition on Z1, and that seems good because now I'm blocking any paths that go from Z1 and eventually lead to Y. Okay. If I condition on Z3, well, that could be bad because now there's a path that goes from Z1 to Z3 to Z2 to Y, right? But I've already conditioned on Z1, right? So that path is closed even though I've opened up a collider at Z3. Okay. So anyway, when I condition on everything, okay, it turns out that x and y are independent. All right. But if I condition, but now let's look at an example where by condition on everything, things are no longer independent. Okay. So so let's look at W and Z2. Okay. Well, I'm going to condition on everything. So before conditioning on everything, W and Z2 are connected, right? There's an open path here, right, from W to X to Z3 to Z2. Okay, so I'm going to condition on everything. So that means that I've blocked that path because I've conditioned on X, and just for redundancy, I've also conditioned on Z3. Okay, but I've also conditioned on Y, and notice that Y is a collider between W and Z2. So now I've actually opened up this path. So by condition on everything, I've actually, W and Z2 are not independent. Okay. So again, you can go through each of these. Okay. All right. Part D. All right. So for every variable V in the graph, where V just is a placeholder for any one of the variables, find a minimal set of nodes that renders that variable independent of all others in the graph. Okay, so let's just start with an example here. Okay, so I'm going to take X, and I want to find a way to make X independent of everything else. Okay. Well, to do this, so let's well, how do I want to say this? Okay, so let's render X independent of Y. Well, to do that, we would use W, and then also, as we saw earlier, we would need to also condition on Z1 or Z3, and then Z1 or Z2. Okay, so that would render X and Y independent. But now I also want to render X independent of, say, Z2 here. Okay. And so, so I can do that by conditioning on Z3, okay? And I want to, okay, so there's all that. Now I also need to render it independent from the adjacent nodes, okay? So I need to condition on Z1, because by condition on Z1 does not vary. And if there is no variance in that variable, then there is no covariance between that variable and X. I hope that makes sense. Okay. So to render X independent of everything else, the minimal set of nodes is W, Z1, and Z3. Okay. Let's do Y also, I guess, for good measure here. Okay, so I want to render y independent of everything else. Okay, so let's first take everything that comes into it. Well, in order to make y independent of w, I need to hold w still. I need to condition on it. Okay, because again, now w doesn't vary, so there is no covariance between w and y because w is not varying. Okay, so I know that I need to condition on w, z2, and z3. Okay, so that's good. By conditioning on w, I block the path from x to w to y, so that seems good. By conditioning on z3, I've blocked the path from z1 to y. Okay, but by conditioning on z3, I've opened the path from z1 to z3 to z2 to y, but I've already conditioned on z2, so that path is closed. Okay, so again, you can go through these for yourself, and again, if I've made mistakes, please let me know. All right. Okay, so now we're at part E and F, so I'm going to answer these together. Okay, so suppose that we wish to estimate a value for y from measurements taken on all other variables on the model. What is the smallest set of variables that would yield as good of an estimate of y as when we measured all variables? So in other words, okay, I measure everything, and I use, except for y, okay, I measure everything, and then I want to see new values of y, right? Or I want to predict new values of y given new values of all of the other variables. Okay, and so it's asking me, could I measure fewer of these other variables and get just as good of a prediction for y? Okay, and then in part E we do the same, but for for z2. Okay, well, we've already answered this actually. Okay, if we want to find a minimal set of variables that gives us as good of an estimate of whatever outcome that we want, well then what we need to do is we need to find the minimal set of variables that renders that target variable independent of all of the others. Okay, so for instance for y, well it's the same as so the answer. The variables that we could measure that will give us just as good of an estimate of y had we measured everything, okay, is the set of variables that renders y independent of all other variables. Why would this be the case? Okay, well so let's look at y here. So we want to so we render independent by condition on w, z2, and z3. Okay, the reason that rendering y independent will give us just as good of a measurement as if we are incorporating everything, right, is because by conditioning on the things that make it independent, other variables, they're independent of y. They make no difference to y once we know the other variables. So for instance, so would it help to measure x if I already knew w, z3, and z2? Well, no, because the only way that x is adding information to y is via w and via z3, and then, well, and maybe via, well, z3, z2, and y, or whatever. But once I know these other variables, there's no additional information being conveyed by x. Okay, so I hope that makes sense. That really part D and then parts E and F are the same question. In a similar way that parts A and B were the same question, just with a particular constraint. Okay. Now finally, part G. Suppose we wish to predict the value of Z2 up here, okay, from measurements of Z3. Okay. Would we get a better estimate of Z2 if we also added W to the mix? Okay. So, so first the answer, and then the understanding. Okay. So the answer is yes. Okay. Why is it yes? Well, it is yes. It is yes because there is information there's information that can leak from W to Z2, and it might not be obvious exactly where that's at, but it goes from W to X to Z1, and then we've conditioned on Z3, and so that is an open collider between Z1 and Z2, right? So we go like this, okay? So there is information, additional information in W about Z2, right? So if I knew a little bit about W, I could make a better prediction of Z2. But there's a little bit of nuance here though, because even though I can make a better prediction on Z2 if I know W, that does not mean that W is somehow a cause of Z2, okay? At least according to the DAG here, right? And so, so this brings up a very important point, which is that prediction and causal inference are very different activities here, okay? So for instance, again, we would be mistaken if we thought that W was somehow a cause of Z2, but that does not mean that there is not information about Z2 contained in W that would help us predict Z2, okay? So anyway, we'll call that good.